Stationary points. A stationary point of a curve is a point on the curve at which the tangent to the curve exists and is horizontal. The diagram opposite shows a curve y equals f of x which has a stationary point at A. So here we have the x-axis, here we have the y-axis, here we have our curve y equals f of x, and here we have the point A, which is the minimum point on the graph, and it is horizontal line. And since this is the tangent to the curve, so a tangent touches the curve at one point, and in this case it touches it at the singular point A, this tangent is a horizontal line, which means it has a slope of 0. And slope is represented by the letter m, and slope is also represented by dy dx, the derivative. So m equals dy dx, which is equal to 0. So here we have a horizontal tangent. So this point here is a stationary point. It's not increasing and it's not decreasing, it's flat. It has a slope of 0. For the tangent to exist at a point on a curve, dy dx must exist at that point. Thus, for example, y equals the modulus of x cannot have a stationary point at 0, 0, as its derivative is not defined at that point. The slope of a horizontal line is 0. Hence, we can restate the definition of a stationary point of a curve as a point where the derivative exists and is equal to 0. Stationary point of a curve. A stationary point of a curve is a point on the curve at which the curve is differentiable and the tangent is horizontal, or the tangent has a slope of 0, or dy dx is equal to 0. So to find the stationary points of the curve y equals f of x, first of all, find dy dx, find the derivative, then put dy dx equal to 0 and solve for x. Any solution is the x coordinate of a stationary point. And then find the y coordinates of the stationary points. So find the coordinates of the two stationary points of the curve y equals 2x cubed minus 3x squared minus 12x plus 7. So our curve is y equals 2x cubed minus 3x squared plus 12x plus minus 12x plus 7. So dy dx, the derivative, is 6x squared minus 6x minus 12. So we put dy dx, the derivative, equal to 0. So we say 6x squared minus 6x minus 12 is equal to 0. And we divide across by 6 to get x squared minus x minus 2 is equal to 0. We factorize to get x plus 1 multiplied by x minus 2 equals 0. So we let x plus 1 equal to 0, so x is equal to minus 1. And then we let x minus 2 equal to 0, so x is equal to 2. So now that we have our two x values, we substitute them into the original equation, so into our curve, to find the y values. So let's start with minus 1. When x is minus 1, we have y equals 2 times minus 1 cubed, minus 3 times minus 1 squared, minus 12 times minus 1 plus 7, which is 14. So one stationary point is minus 1, 14. And then we're going to substitute 2 into our curve. So we have y equals 2 times 2 cubed, minus 3 squared times 2 squared, minus 12 times 2 plus 7, which gives us y is equal to minus 13. So the other stationary point is 2 minus 13. So the point minus 114 and the point 2 minus 3 are the 2 points on our curve where the tangent has a slope of 0. There are 3 types of stationary points shown in the diagram opposite as the points A, B and C. So A, B and C. 2 of these, A and B, are called turning points. So A is a turning point and B is a turning point. C is not. So 2 of these, A and B, are called turning points as the curve turns around at these points. So you can see for A, the curve was going upwards, it was increasing, and then it turns and it starts going downwards, it starts decreasing. At B, the curve was going downwards, it was decreasing, and then it turns and starts going upwards, it starts increasing. The third, C, is not a turning point, but it is a point at which the tangent goes from one side of the curve to the other, i.e. the tangent cuts across the curve. Each of these 3 points has its own name. So A is a local maximum point. This is the highest point on the curve in the locality of A. It may not be the highest point overall. At a local maximum point, local max for short, the curve goes from increasing on the left to decreasing on the right. In other words, dy dx goes from positive through 0 to negative. So increasing on the left, then it has a slope of 0, and then it's decreasing. B is a local minimum point. This is the lowest point on the curve in the locality of B. It may not be the lowest point overall. At a local minimum point, local min for short, the curve goes from decreasing on the left to increasing on the right. In other words, dy dx, the derivative, goes from negative through 0 to positive. So it's decreasing, then it has a slope of 0, and then it's increasing again. C. C is a saddle point or a saddle point. It's a horizontal point of inflection. At a saddle point, the curve is increasing on both sides or decreasing on both sides. In other words, dy dx goes from positive through 0 to positive, or negative through 0 to negative. So let's have a look at this saddle point. So we can see the curve is increasing, then it evens out, and we have a slope of 0, and then it starts increasing again. So it's a saddle point, it's not a turning point. These observations form the basis of the first method called the first derivative test for determining the nature of a stationary point. The first derivative test for stationary points. First of all, if dy dx goes from positive to 0 to negative, then the point is a local maximum. Secondly, if dy dx goes from negative to 0 to positive, then the point is a local minimum. And thirdly, if dy dx goes from positive to 0 to positive, or from negative to 0 to negative, then the point is a saddle point. In practice, we take sample values of x on each side of each stationary point. By evaluating dy dx at each of these values of x, we can determine the nature of each stationary point. This can be laid out in the form of a table as shown in example 2. Find the stationary point of the curve y equals x cubed minus 6x squared plus 12x minus 5 and determine the nature of this stationary point. So y equals x cubed minus 6x squared plus 12x minus 5. The first thing we want to do is find the derivative, dy dx. This is the first derivative test. So the derivative is 3x squared minus 12x plus 12. So we can factorize out the 3. So we get 3 times x squared minus 4x plus 4. And then we can factorize what's inside the brackets. Factorizing x squared minus 4x plus 4 gives us x minus 2 squared. So we have 3 times x minus 2 squared. We're going to put dy dx, which is the derivative, equal to 0. So we have 3 times x minus 2 squared equals 0. So we can divide across by 3 on both sides. So we get x minus 2 squared equals 0. So therefore, we have x minus 2 times x minus 2 equals 0. So just taking one of them, since they're the same, x minus 2 is equal to 0, so x is equal to 2. So x is equal to 2 and y is equal to 3. Because what we do is we take the 2 and we substitute it into our original equation, into our curve. So we have 2 cubed minus 6 times 2 squared plus 12 times 2 minus 5, and that gives us 3. So that's where we get the y value of 3. Thus, the stationary point is 2, 3. So this is our curve, and we know that we have a stationary point at 2, 3. Now we need to find out the nature of the stationary point. Is it a local max, a local min, or a saddle point? So what we do is we take x equals 1 and x equals 3 as sample values on each side of x is equal to 2. So our x value was 2. So this is our little table here. And the top row is our x values. So since we know that x is equal to 2, we let one of our x values be 2, and we choose an x value either side of the 2. So 1 less than 2 is 1, and 1 more than 2 is 3. So now we have our x values 1, 2, and 3. So at x is equal to 1, dy dx is equal to 3, which is positive. And this is because we take our derivative, 3 times x minus 2 squared, and we swap the x for 1. So you get 3 times 1 minus 2 squared, which gives us 3. We're not interested in it being 3, we're just interested in that it's positive. So when x is 1, dy dx is positive. We already know that when x is 2, dy dx is 0. And now we want to check what happens when x is 3. So when x is 3, dy dx is also 3, which is positive. Because 3 times 3 minus 3 squared is 3. Again, we don't really care that it's equal to 3, we're just interested in the fact that it's positive. So when x is 3, dy dx is positive. So a positive slope looks like this, an increasing shape. A slope of 0, we have a horizontal line. And a positive slope, again, we have an increasing slope, which looks like this. So we can see that we are increasing, then it levels off, and then we're increasing again. So from the table, 2, 3 is a saddle point, otherwise known as a horizontal point of inflection. So we've gone from positive slope to slope of 0 to positive slope. So we know we've got a saddle point. If we'd gone from negative slope to 0 to negative slope, we would also have a saddle point.